this is an excellent example of a chi-square practice problem because it involves a bunch of different considerations that you have to make when solving these. The problem reads, another fictitious mutant, bloodshot eyes, is hypothesized to be autosomal recessive. The experimenter used homozygous wild-type virgin females, but this time the males had homozygous bloodshot eyes. The F2 generation data was 75 wild-type males, 60 wild-type females, 31 bloodshot males, and 45 bloodshot females. Does this data support or reject the hypothesis? So before we go into the problem, let's look at a few things that are indicated in the problem as it's written. First is that we're dealing with a mutation that we think to be autosomal recessive. And that's really important for this problem. The fact that it's autosomal means that you don't have to consider the differences in the sexes. All right? Secondly, we're considering F2 generation data. All right? So let's try to set up the chi-square problem. If you were to just set up the problem using your Punnett squares to get your expected values for this data set, you would indicate that you're dealing with a homozygous dominant individual being crossed with a homozygous recessive individual, right? So this, of course, is for the parental generation. And after those two individuals are crossed together, you end up with your F1 generation, where you'll have 100% of the offspring being heterozygous. What the problem then implies that you should do is cross these F1 generations with one another. So we're crossing our heterozygous individuals from the F1 generation with heterozygous individuals from that F1 generation. Okay? This cross, if you do a Punnett square, you'll see should result in 25% of the individuals being homozygous dominant, 25% of the individuals being homozygous recessive, and 50% of the individuals being heterozygous. But since we're only dealing with phenotypes in this question, we can lump together the homozygous dominant and the heterozygous, and we consider them to be of dominant phenotype, which I'll represent as just being a large E. Okay, so 25% of the individuals should be recessive phenotype. The tricky thing with chi-square analysis is that you can never use percentages. Rather, you have to use counts. Okay? So in our experiment, we indicated that there were 75 wild-type males, 60 wild-type females, 31 bloodshot males, and 45 bloodshot females. Okay? And if we sum all of those numbers together to get our total population, we end up with a population of 201 individuals. Okay? To get the expected values of these different phenotypes, and remember, we can sum together the wild type and the mutant phenotypes, and whenever we do that, we get 75 plus 60, 135 wild type, and 31 plus 45 gives us 76 mutant individuals. All right? To get our expected values, what we have to do is we have to multiply 75% and 25% times 211. And whenever we do that, we get 158.25 expected individuals for our wild type phenotype, and 52.75 individuals for our expected mutant phenotype. To run our chi-square analysis, we have to use the chi-square formula. And the chi-square formula states that chi-square is equal to the sum of observed minus expected squared over expected. The easiest way to set these problems up is using a table, because it allows you to work through the problem step by step. So what I'm going to do first is put the phenotypes, which are the wild type phenotypes, and the mutants serving as two rows of this long table. And the columns of the table will be each one of the steps of this problem. So I'm going to have one column for my observed phenotype, one for my expected, one for the quantity observed minus expected, one for the quantity observed minus expected squared, and one for the overall function observed minus expected squared divided by expected. Okay. Now, we observed 135 wild-type individuals, but we expected 158.25 wild-type individuals. We observed 76 mutant individuals, and we expected 52.75 mutant individuals. So now I'm going to subtract the expected from the observed, and I get negative 23.25 for my first row, and then conversely I'll get 23.25 for my second row, for my mutant row. Next, I'm going to get the absolute values of these two numbers by squaring them. Which is 540.56 for both of them. And then I'm going to divide these values by the expected. So I'm going to divide 540.56 by 158.25. For the first one, which is 3.41, and then divide 540.56 divided by 52.75, and that gives me 10.25. Now, because chi-square is the summation of the observed minus expected squared divided by the expected, I'm going to take the values in this last column, add them together, and that's going to give me my chi-square statistic. And whenever I add those values together, I get 13.66. This is equal to my chi-square statistic, but we're not finished quite yet. What we have to do next is determine the degrees of freedom. In this example, because there are two rows on our chi-square table, there is 1 degree of freedom. Because the degrees of freedom are equal to the number of rows minus 1. And in biological examples, that usually translates to the number of phenotypes minus 1. And because we're tracking two different phenotypes, wild type and mutant, the degree of freedom in this analysis is equal to 1. All right? To finish the problem, we have to look at a chi-square table. And a chi-square table contains values of chi-square based on the number of degrees of freedom. All right? In our problem, we said that we have a single degree of freedom, so we're going to narrow our focus to this topmost row on our chi-square table. And our chi-square value, if you'll remember, was well over 13. And since the highest value in a single degree of freedom on the table is 7.88, we know that our p-value would be rightward of 0.995. So what does that mean? If you consider a chi-square distribution with a single degree of freedom, it'll have a shape similar to an exponential decay function, okay, with chi-squared values on the x-axis and the y-axis essentially being the counts of this function. A chi-square value of 13 would be pretty darn rightward on that distribution, okay? And that means that the probability of the null hypothesis is the area underneath the curve in our chi-square distribution. So we can call this P sub h naught for the probability that our null hypothesis is true. Conversely, that means that the area to the left of our chi-square value is the probability that our alternative hypothesis is true. Okay? Because the probability lies beyond 0.995, we can assume that the probability of h is greater than 0.995, and the probability of h naught, therefore, is less than 0.005. Okay? Because the probability of the h naught is so low, we can reject h naught. And the h naught in this case is the hypothesis against which we are comparing our data. And that hypothesis is that this data set is due to autosomal recessiveness. Because the data set deviates so significantly from autosomal recessiveness, we can thereby determine that the null hypothesis, that this is simple autosomal recessiveness, is not correct.